Hey everyone, welcome back to the channel. Today we're going to be going over the AAMC free practice exam CP passage 4. If you're not familiar with the channel, my name is Maggie. I was a professional MCAT tutor before I started medical school, and me and my brother John run this channel. We have a lot of cool projects going on like all the time that you can check out in the link in the description below. But first things first, let's get to this passage. Okay, so this is CP. So the things that we want to pay attention to are basic sciences, units, graphs, are sort of important. Well, they're always important, but like sometimes they're more important in stuff like psychosocial. And making sure that we don't get too bogged down in like big words or acronyms that we can't remember and stuff like that. So let's just go ahead and start reading. Thiopurine S-methyltransferase, TPMT, is an enzyme that is responsible for the metabolism of the drugs azathioprine and 6-mercaptopurine, which are used to treat acute lymphoblastic leukemia and inflammatory bowel disease. So some things that you may have to know about enzyme. You probably won't have to know anything about drug metabolism or leukemia or IBS or these drugs. Just noticing that that's an enzyme and specifically a methyltransferase. So we're going to be transferring methyl groups. Metabolism by TPMT reduces the bioavailability of the drugs. In addition to the thiopurine substrates, TPMT also binds S-adenosyl methionine as a cofactor. Okay, methionine is an amino acid, right? We have to know a little bit about cofactors, just kind of like that they're there. But they could spin this and ask a question sort of about that. TPMT is a highly polymorphic enzyme. Almost 30 variants are known to be expressed in humans, with most of the variants possessing lower enzymatic activity than the wild-type protein. Despite having substitutions remote from the active site, TPMT2, an A80P variant, and TPMT5, an L49S variant, have enzyme activities of 47% and 14% relative to the wild type at 18 degrees Celsius, respectively. So you do need to know, like, these come up all the time, and like it took me a while to understand what they were saying. So this means that at the 80th position, because they number, in proteins, like they number each amino acid. So at the 80th position, it used to be an alanine and now it's a proline. And here at the 49th position, it used to be a leucine and now it's a serine. Y'all, I haven't thought about these amino acids in a minute. So definitely know how to read that kind of stuff. They'll ask questions about it all the time. So basically having any kind of variant is going to drop your enzymatic activity as opposed to the wild type, even though these variants are highly prevalent in the population because it's a polymorphic enzyme. Two techniques were used to understand the relationships between enzymatic activity and protein stability. Circular dichroism, CD, spectroscopy, measures the differential absorption of left and right circularly polarized light. So we should know a little bit about polarized light, right? And chirality and all that kind of stuff. And is used to examine the secondary structure of proteins. That's protein structure is high yield, so definitely they could ask a question about this. The thermal denaturations of all the enzymes were followed by CD spec at 222 nanometers. So there's some units we could use. I'm going to look quickly at this figure. It says thermal denaturation of the proteins followed by CD spec. So we have this key right here tells me that the regular line is wild type. The dashed is the 2. And the dotted is the 5. And we got fraction and folded increasing over here and at temperature. So it looks like it's looking at stability maybe. And that we see kind of that these two, let's see, the 5 and the wild type seem to be a little bit more stable, but wild type is the most stable because it takes more temperature to denature it. To analyze the relative flexibilities of different regions of the TPMT proteins, the proteins were incubated with chymotrypsin, which preferentially cleaves at aromatic and bulky hydrophobic residues. So they could ask us totally like, where does chymotrypsin cleave? And you'd have to pick an aromatic and bulky hydrophobic residue. For lengths of time ranging from 0 to 200 minutes. Okay, so I didn't flowchart anything because this was mainly like a basic science kind of passage. Like, I did highlight a bunch. They could ask some good questions about amino acids. They could ask some stuff about protein structure or something where we have to do a little bit of math with nanometers. So I think we should probably just get into the questions. Because I don't know what like circular dichroism is. I don't know exactly what these drugs do or anything like that. I don't know how leukemia works. You don't have to. You just have to know the things that are highlighted. Number 17 says the CD spectroscopy signal that was used to generate the data in figure 1 arises from the chirality of the... So if we were to reword this question, CD spec, we know, was dealing with chiral carbons, right? To examine the secondary structure of proteins. So this question is essentially asking, what is chiral in a protein? And what is the only thing that is chiral in your basic amino acid structure? For every amino acid except for glycine, it is the alpha carbon. The amide nitrogen is not because it has two or three hydrogens coming off of it, and so it doesn't have different groups. The carbonyl carbon is sp2 hybridized, and the beta carbon is like the first atom in the side chain, and so it kind of depends. I can't actually think of one right now that might be chiral. Maybe something weird like tryptophan or something might be chiral. I don't really know. But regardless, you need to know that the alpha carbon of amino acids is chiral in every case except for glycine. Number 18 says, which physical property does not change with the amino acid substitution made in TPMT5? So let's go up and see what that amino acid change was. So in TPMT5, it is L to S at the 49 position. So this is leucine and this is serine. Is there going to be a difference in molecular weight? Yeah, right? Like it's hard to not have a difference in your molecular weight. Is the hydrophobicity going to change? Yes, right? So leucine is a non-polar, and serine is kind of like riding the fence, but it's more polar than it is non-polar because it's got this hydroxyl group on the end right there. So the polarity or the hydrophobicity is definitely going to change. The hydrogen bonding capability, absolutely going to change, right? Because that's a big deal about serine. It can be phosphorylated and it can hydrogen bond. So that's a big deal. Leucine cannot do that other than like its backbone, but that's not really what it's talking about. It's going to be talking about the side chain difference. And so absolutely that would change. The net charge. So the net charge of both of these is going to be 0. And so that is not going to change. Again, know all of these properties. I mean, you don't have to know the molecular weight of anything, but know all of these properties for every amino acid and be able to draw them out and know their 1-letter and 3-letter code. So next question, 19, says samples from various time points of the proteolysis of the enzyme were subjected to SDS page under reducing conditions. Which figure best depicts the expected appearance of the gel? The arrow indicates the movement of protein through the gel. So I started thinking about like what are the products of the proteolysis, and like that's going to be important because I need to know like the molecular weight and the charge to know how it gets through. And probably some of y'all started going down that rabbit hole too, but I encourage y'all look at these answer choices. There's only one that even like makes sense if you know how SDS page works, and SDS page works by filling different wells. That's what these little bars at the top are called, wells, with, in this case, it'd probably be the protein with the enzyme. If I'm wrong about any of this, it's probably like a smallish detail. Like I can get this answer choice right, but I am going to try to explain what SDS page is. So you fill these wells, I think in this case, probably with a protein and the enzyme that's going to like cleave the protein into lots of different pieces. These pieces are going to be charged in different ways. And then you run a current through the gel, and you let these pieces kind of move throughout the gel. And the smallest ones are going to move the fastest because there's gel in here that makes it kind of like sticky and thick. So the smallest ones are going to move the fastest. And also, depending on where your cathode and anode are, different charges are also going to move faster. And that just follows general electrochemistry laws, like opposite charges attract. But honestly, like you only have to know like the basics of the setup of SDS page to get this question right, because the wells are going to be at the top. Like they're not like A and B show the wells at the bottom of the plate, and that's not right. And you know it's the bottom because that's where the arrow is. C shows the wells in the correct place, but if you'll notice, like it looks like this gel electrophoresis is already run, and so you wouldn't still have anything left in these wells if it's already like down here. Does that make sense? It's going to look like D. So over time, you were going to see that well decrease in size as its constituents move down the gel. So it's going to look like D. So you really didn't have to know anything about the products of the proteolysis of TPMT and all that stuff. Like, you didn't have to know that. Thank goodness. That would have made this question a lot harder. Number 20 says, if the combined mass of the TPMT substrate and cofactor was determined before the enzymatically catalyzed reaction and then compared to the combined mass of the product and the cofactor after the reaction, the net change in molecular weight would be, okay, this is a lengthy question. But the moral of the question is, how does a molecular weight change as a result of what TPMT does? I want to know what TPMT does. So we were not really told in great detail, but okay, so some things that we do know. It's a methyltransferase. It's transferring a methyl. It uses its thiopurine substrates and this as a cofactor. Do we know like the molecular weight of any of those things? No. We do know, I think where they're getting this 15 grams per mole is that's the molecular weight of a methyl group. Because C is 12, or carbon is 12, and then H is 1, and there's 3 of them. So that equals 15 grams per mole for a methyl group. So I think that that's where they're trying to trip you up. Let me ask you this question. Where does the methyl group go? Were we told? I'm guessing it's been taken from the substrate. Is it put onto the cofactor? I don't really know. I don't know where it goes. It could be put on the cofactor. And that's probably actually going to be like our best bet, because like I don't know where the methyl is coming to and where it's going to. So we can probably mark out D, right? Because that's not the weight of anything. But it's really hard for me to say that I know that. Like, I guess technically the methyltransferase could bring in a methyl to the thiopurine. Like, it's just, I think it's impossible for me to say. And so my best guess here would be that it doesn't change. And I know y'all probably don't like that explanation. I don't really like that explanation. But without any more data as to where that methyl is coming from or where it's going, I think it's the safest bet to say that it is staying within the molecules that have been described in the passage. And so if we are taking into account the weight of the substrate and the cofactor both before and after the reaction, then there probably is not going to be a change in molecular weight. All right, so that wraps up that passage. It's easy to see how CP passages that sound so complicated when you're reading through them can actually have some fairly straightforward questions like what's polar or what's chiral in an amino acid. Stuff like that. So just stick to your guns, stick to your basic sciences when you're reading through them, and don't get bogged down in all the details, and you'll be just fine on CP. If this passage was helpful, please hit like and subscribe so that we can keep making these kind of videos for you guys. Comment down below what you want to see next, and I will see you on the next passage.